Okay, welcome back everyone to lesson 3 where we're going to look at voltage dividers. This one's a little bit shorter. Let's see how we go. Alright, so we're on page 17 of our notes. So in this section just here, have a read of the theory, but we've got an overall voltage in the circuit and we've got multiple devices consuming the electromotive force. So the voltage is going to be split into various sections. And because we've got a series circuit, all of the voltages need to add up to the total. So in a series circuit, the voltage is cumulative. This can be applied to Ohm's law. Remember, Ohm's law is V equals IR. And if you rearrange this for the current, you'll find that the resistance just goes underneath. And it's just basically saying you've got multiple resistors. So that's where this value here comes from. Okay, straight into the questions. Let's punch through these. Here's our circuit, multiple resistors. We want to know how much voltage drop there is between this point and this point. So we've taken our electrical probes and we're probing either side of this first resistor to see how much voltage drop we have between this location and this location. Okay, so we know that the voltage, the total voltage is 30. And we know the resistance here is 5,000 ohms. And the output voltage is 6. So I've got our probes and the voltage here is 6. So using V equals IR, I can rearrange this equation for current to find out how much current is flowing through this circuit. So to find I move R underneath. And we're talking about section 1. And I know the voltage was 6 and the resistance was 5,000. Six divided by 5,000. There's my current. We've got 0.0012 amps. Now, we're in a series circuit. What do I know about current? It's constant. So the amount of electrons flowing through this part of the circuit is identical to the amount of electrons flowing through this circuit section just here as well. So I know I up here is also 0.0012. If I want to know the voltage, well, I need to know that all of these numbers need to add up to 30. So I've got 6 volts here, therefore I've got 24 volts left over. Now using these two values, we should be able to work out the resistance using Ohm's law. From V equals IR, I want to know the resistance, so move I underneath. We're looking at section 2 of the circuit, so we're going to use V2 and I2. So what's 24 over 0.0012? And this should be fairly easy to just think about logically by just looking at the voltage. The voltage drop here is 6 and the voltage drop here is 24. So there's 4 times as much force going through this section of the circuit. And remember, resistance, I need to think about resistance like pressure. So I've got 4 times as much force going through this part of the circuit, so 4 times as much pressure, i.e. the resistance in here is 4 times as much because the voltage is 4 times as much as well. So if I know the resistance just here, when I put that in the calculator, it should be 4 times this number. So 20 kilo ohms. (24) divided by 0.0012. Genius. and I'll box my answer. Okay, question 50. We're going to use the same circuit again, but this time we only have 10 kilo ohm resistors to work with. Explain how you construct the circuit so that we still have 5 kilo ohms resistance happening through here. Well, this is fairly straightforward. Instead of having one electrical pathway, what we're going to do is we're going to split it into 2 electrical pathways. So generally we only had one pathway for the electricity to flow. But now if we have 2 pathways for it to flow, half as many electrons will travel through this section and half as many will travel through that section. So we still have the same number of electrons flowing through our circuit as previous, but this time only half as many go through each section. So because there's half as many electrons flowing through each section, there's half as much force flowing through each section, or half as much pressure. We've halved the pressure. So if each one of these has a resistance of 10 kilo ohms, their effective resistance is actually half as much, because there's only half as much force flowing through that section of the circuit. So here's my diagram to complete this section. So you would place 2 10 kilo ohm resistors in parallel. If it asks for a definition as to why, well, 2 pathways means there's going to be half as much force through each pathway, so half as much resistance. Okay, question 51. In the circuit above, we have a simple voltage divider where we've got a voltage total of 15, and we know the voltage, we want the voltage out to be 5 volts. And we know R1 is 1000 ohms. All right, what is the resistance just here? So that the voltage here is 5 as required. Well, if the voltage here is 5, that means that the voltage here has to be 10. And let's do this one without any equations quite logically. If the voltage here is 10 and I want the voltage here to be 5, well, that means I need half as much flow of electrons. I need half as much pressure going through this section, through this resistor. So instead of having 1000, I want half as much as that. So the resistance should just be 500. Okay, I've got a more complex circuit underneath now. This one has a switch which can be opened and closed. So currently now the switch is open and we want to know what the voltage is between this location and that location. So let's have a look where the circuit flows. Here's the negative terminal. So electrons always flow from the negative terminal. And it goes up and then it splits into 2 pathways and then it comes back through. So the electricity can't flow this way because we've got a break in the line. So we want to know what's happening to the voltage just here. And it says up the top that all three resistors have the same resistance level. So up here, we've got two resistors in parallel. So I've got a fork where the electricity splits from one pathway into two pathways. So because the electricity splits into two pathways, there's half the amount of resistance in this section of the circuit compared to over here. If I have half the resistance, I've got half the voltage because I've got half the amount of force pushing through because the force is spread out over both of these pathways. So the voltage here is going to be half as much as it is here. And I need to think about this here as really one device for an effective, because really in parallel, we've only got one circuit, but this is as an effectively one voltage, because if we are in a parallel, you can see voltage is constant. So this number is twice as big as this number. And I know the total voltage is 15. So what two numbers work so that this number is twice as big as this number? And it turns out we get 10 and 5 for that to work. So the voltage here is 10, therefore the voltage here will be 5, because it's got half the amount of resistance, effective resistance. So the output voltage, we want to know this bit, is going to be 10. Okay, a little bit more difficult now. The switch is closed. So we close up that switch. We want to know the output voltage. Well, if this switch is closed, we've got a bit of a problem, because the electrons can flow previously through a device that wants to consume electromotive force and then travel back around. But when this switch is open, we've effectively short-circuited the parameter, because there's no device in here that's consuming power from here to here, back to this original circuit. So instead of the circuitry wanting to go through this device, I've made a short circuit. So instead of flowing through a device that consumes power, the electricity is going to choose to go this way and divert itself so that it does not flow through this electrical device at all. So by short circuiting it, we've got all the electricity flowing through this section, and this section here is bypassed entirely because there's no resistance at all through here compared to here. Ignoring, of course, the resistance in the wiring itself. So we have a short circuit, so the output voltage will be 0. Okay, in our next circuit we have 5 resistors, and they're all 100 ohm resistors. We know that the voltage source is 20 volts. We want to know the output from here to here. So how much force is consumed from this location, here and here? So I need to know the voltage drop here, and I need to know the voltage drop here, and then I need to add them together, and that will tell me the total voltage out. Well, let's assume that the voltage here is V through this section. In this first section, we've had the flow of electricity divided into 2 sections. So the electricity is split, so the voltage is split because the resistance is half as much. So the amount of voltage flowing through this section is only half as much as this section just here. And you'll see that A and B is also identical down here. So this is also half as much as well. So in total, the total voltage is 2V. 1 plus a half is 2. So in this section, V would be 2 times 10. Pardon me. So the voltage here is 10, and because it's split into two identical pathways just here, I know the voltage here will be half as much. So the voltage here will be 5. So the total voltage will be 15. Now, a common mistake for this section would be to say that, the voltage over here is 5 as well. So the voltage drop from this location to this location is 20, because 10 plus 5 plus 5 is 20. But you're forgetting that this section of my circuit is split, so it's in parallel. And in parallel, I need to remember that voltage is constant. So there's an effective 5 volts flowing through this circuit, in this part of the circuit just here. Okay, last question, question 55. Now I've looked ahead and question 55 appears to have multiple correct answers, whereas the answers at the back only say there's one correct. Which one of the following statements concerning current is true? We're dealing with this circuit up the top. So the current flowing through resistor A is identical to the current flowing through here. So let's think about this circuit just here. Yes? Just here, we've got this is a series circuit. So I is constant. But in this section just here, it splits into two sections. So we've got a parallel circuit. So in a parallel circuit, the current adds up. So the total current is equal to this section just here, but individually the current here is actually half as much. But when you add the cumulative currents, because remember half the electricity flows this way, half the electricity flows that way, so you're going to get half as much current flowing through this section because the electricity is split. So A is indeed wrong. All right, B. The current through resistor D is twice as much as C. Well, no, it's actually half as much because remember the electricity is split in half just here, so half as much current is flowing through. The current in B is twice as much as E. Well, that's no again. This is the current divided in half, and this is also the current divided in half, so really B and E should be the same. The current in A is identical to that of D. That's true, because half the current flows this way, and then it recombines, and then again, half the current flows in this way as well. So the correct answer there is D. Okay, that one was a nice short lesson. I hope for again, reminder that we are pausing the video for every single question and attempting them before moving on to the next section. So making sure that we are doing that. Okay, stay tuned for video 4, where we're going to be looking at devices that do not obey Ohm's law. So no using V equals IR. You can't use this, you've got to use a measured graph.